first of all, I would like to thank kindly to the organizers for this opportunity to being here and to talk about one of my research projects about topological states and fractal lattices. So this work has been done in collaboration of Ashley Cook, who is currently a postdoc at UC Berkeley, and my supervisor from University of Zürich, Titus Neupert. So for those who are interested in more details about this work, there are it was published at the end of 2018 in PRB. Okay, so the outline of my talk is as follows. First of all, I would like to motivate why we were interested to study potential existence of topological states on fractal lattices. Then I would like to be more precise about what we studied and also what type of methods we've been used, since this field of research is still not discovered in very details. And finally, I would like to sum up and also point out some further directions which I find very interesting. Okay, so today in the morning we had really nice talks about extension of classification of topological insulators and superconductors, what type of methods we can use to also make some predictions in real materials. But obviously, all the time, the starting point is the so-called tenfold way, in which we have the presence or absence of internal symmetries, such as time reversal, particle Hall, and chiral symmetries. Also, this classification is based on the dimensionality, so depending in which spatial dimension the system lives, then we can make use of this table and predict potential topological properties. In recent years, there's been really an immense effort made to also include crystal symmetries and make this classification, the tenfold way, even more refined. So, for example, by thinking about like rotation symmetries or reflections. So this is still a very ongoing topic, how to make even more complicated tables. Another direction is actually including non-hermiticity in the systems. Because if we relax the condition that our Hamiltonian has to be Hermitian, then we also allow for, to introduce new class of symmetries, which are only seen in non-Hermitian systems. So as you can see, these are the very recent works on that. However, in all those cases, what we can do is we can actually think about Bloch Hamiltonians and reciprocal space, because we can build models with some of given those symmetries, assuming that there is a translational symmetry. However, what we know is that it's not a necessary condition to have a topological state. That is, topological states can also exist in systems, in aperiodic systems. For instance, there were really nice experiments, for example, on photonic quasicrystals. So quasicrystals do not have this translational symmetry as ordinary crystals. Also, we can observe some topological states in completely classical systems. This is actually made of mechanical gyroscopes. Also, there are very nice predictions from theoretical perspective, that is on such tilings. We can, for example, observe topological superconductivity, or even we don't have to have any lattice, just a set of random points to observe topological states. Another motivation is that what if we don't have a clear notion of the edge and the bulk? So what if our system is, for example, consisting mostly of the edges? Then the problem is actually how to define where is the bulk and where is the edge, and how to, for example, make use of the bulk boundary correspondence. Also, another interesting issue that may appear is that there are some set of systems which are actually like self-similar systems that don't have to necessarily live in an integer spatial dimensions. And if we would like to answer to those questions at once, the answer is the fractals. So the fractal geometries are really like a natural candidates to actually investigate those questions. And I assume like all of you have seen fractals, so I don't want to show a picture of broccoli, but what I would like to show is actually the recent progress in fabrication of such lattices. So, for example, here in the corner on the left, we can see, using focus ion beam method, a set of gold particles which are assembled to show Sierpinski carpet structure. Also, some other works are using molecules. For example, here we have CO molecules on a copper surface, or also very complicated molecules, which names I unfortunately cannot repeat because they are very lengthy, but still you can really create fractals in a lab. So this is also another motivation why we would like to study such systems, because really they can be fabricated in a lab. Okay, so our main goal was to investigate integer quantum Hall effect living in fractal dimensions. Why actually integer quantum Hall effect? The reason behind that is that we know that this is like a prototypical example of topological phase. It also does not require any symmetries and is seen to be as the most robust example. So we are considering this very simple Hamiltonian with spinless fermions exposed to external magnetic field. So here we have only nearest neighbor hoppings and the phase acquired due to the presence of magnetic field. And we would like to build this Hamiltonian on two lattices that are called Sierpinski carpet and gasket, or triangle. This is also another name for gasket. And how we would like to, first of all, build such lattice in the formalist mode of tight binding. So in both cases, we are starting from the regular lattices. So the square lattice or a triangular lattice. And then in every step, in every iteration, we would like to extend our system size and remove some lattice sides and hoppings. So it's slightly different approach than what we know from mathematics, that like perfectly nicely defined mathematical fractal is scale invariant in any sense that no matter how zoom you into your picture, you still will have this self-similar structure. But we wanted to have some connection to reality. So if we think about this experimental realization, it's obviously very natural to think about some cutoff, some smallest distance between neighboring sites. So with this approach, that with every iteration, with every step we make our system more complex, we simply increase the system size. Why actually those two lattices? The first thing is that they have different, the so-called Hausdorff dimension. So Hausdorff dimension is defined as here. This is the logarithm of the area over the linear length of our system. And in case of carpet, it's 1.89 roughly, which says like it's almost two-dimensional system. However, when it comes to the gasket, it's 1.59. So this is really not that two-dimensional anymore. Another very interesting difference between those two systems, actually this is a property in the thermodynamic limits, is the so-called ramification number, which means that when we are in the thermodynamic limit, how many cuts we have to perform in order to get smaller part of a fractal from the whole structure. So it turns out that for the carpet, you have to do infinite number of steps, but in case of gaskets, it's a finite number. So this concept of connectivity is also different for both those two lattices. Okay, so as a test, first of all, we would like to take a look on the spectral properties. And our first result was to plot the energy spectrum in energy magnetic flux plane. So for the regular lattices, we know that this gives rise to the so-called Hofstadter butterfly, so the self-similar energy spectrum. And indeed, a very nice, we have basically fractals on fractals in that case. So these are the results on the left for the carpet, and these are the results for the gasket. So for example, just by investigating the spectra, we can see, like for example, there is a symmetry along line E equal to 0, and also along magnetic flux being 1/2. Here, in case of gasket, we have like numerous gaps, but like symmetries only with respect to this inversion point here. And in case of carpet, we have some gaps here, but also low density of states regions here. So, as I said, we are investigating systems without translational invariance. So these are results just for finite flakes. We wanted to also check the localization properties of eigenstates. To do so, we picked some few consecutive states from the very middle of the spectrum. And we will see that there is some hierarchy of localization of eigenstates. So, for example, even those states are very close in the, like they are in a spectral proximity. They really have energies, very similar energies, but the localization properties are completely different. So what you can see is that indeed, due to magnetic field, states are localized on internal edges of fractals. And this is indeed the effect of magnetic field. So if you would like to plot the density profile without magnetic field, you won't see such features. Okay, but this is not surprising at all that we have some edge modes, some states which are localized on the edges, mostly since our systems are consisting mostly of edges. So we would like to also make some predictions in a quantitative manner. And to do so, we calculate the so-called edge locality marker, which is nothing but just localization of some states on some sites I, and labeled by the eigenstate label lambda. Okay, so how this quantity works? So L corresponds to the level or hierarchy in our system. So I don't know if you can see, but there is a difference between orange and red here. So let's just, so basically like one level of hierarchy is those larger squares. Another set of edges are marked with an orange. Also, there is like a green one. The same hierarchy we can build for a gasket. And what we would like to do is to calculate the variance of this quantity for a set of 3 consecutive eigenstates. This would give us information how rapidly the eigenstate localization properties vary. And these are the results for the variance. And we can see, like, for example, here, the low density of states regions are actually characterized by this rapidly varying hierarchy of edge-localized states. So that was like a really interesting feature, but we also would like to finally say something about topology. And as I said, we don't have the access to reciprocal space, so we have to think about other ways how to compute some topological invariant. And actually, what we can do is we can take a look on Kitayev's paper, check the appendix, and find this very nice formula, which is based on the projector operator on the occupied space. So how does this formula works? Let me just give you an idea. So suppose we have some lattice. So those blue dots are corresponding just to lattice sides. And we encircle some region, some finite region, which then we divide into 3 pods, A, B, C, and those pods are arranged in counterclockwise manner. And then you can see that indices J, K, and L, given in this antisymmetric product, are actually corresponding to lattice labels from those regions. And these are the results for a fixed flux in case of carpet, in which we use this formula and calculate for different occupations. So what you can see is that indeed there are some nice plateaus with a very nicely quantized real space Chern number. And you see, like, there are some peaks which are actually corresponding to enhancement of density of states. But overall, this quantization here and here is like 0.99. Also, one may ask how robust is the way we are calculating the Chern number in that way. So here, what I am showing is the Chern number from two regions of energy. So in case when we have like nice quantization and not so nice, we can see like when indeed we are in this plateau, then the Chern number is quantized almost all the time, no matter how large we make this finite patch, so no matter how many elements we include in this product. However, when there is like a poor quantization, like for example here when we have a Chern number being 0.9, then unfortunately one has to optimize the size of the finite patch. And also, like, one may ask, well, Chern number is supposed to be an integer. This is something which we learned from. But as I said, most of the time we are dealing with low density states of regions. They are not fully gapped. So for example, in this part where there is a gap at 0, it's actually quantized. Okay, so thanks to those calculations, we have some intuition that indeed there may be some topological phase realized on those lattices. However, we would like to make another like ultimate probe just to observe potential disorder-induced phase transition. So basically what we know is if we add enough disorder to our system, the states become Anderson localized. So we would like to then calculate the level spacings, which are defined as follows. So for each disorder realization, and in that case, we focus only on on-site disorder, which was drawn from a symmetric distribution with a strength W. So for which epsilon, for each epsilon, we just finding the energy states which are very close to this value, so just one below and just one above. And then we calculate the difference. And we perform the same procedure for different epsilons. So therefore, we have like quasi-continuous number of epsilons for each disorder realization. Obviously, we can also take into account not only nearest neighbor spacings, but also next nearest neighbor. That's the reason there is the index M. However, we check that this does not change much results. Okay, and then we would like to calculate the variance. And the reason to do so is that we can make later on the use our knowledge from random matrices theory and see whether we have delocalized or localized states. So in case of delocalized states, the level spacing distribution should supposed to follow Wigner-Dyson, which is drawn here with a green line, with a variance being equal to 0.17. However, if states are localized, then they obey the Poisson distribution with just a large value of variance. Okay, so just to sum things up, I would like to show all results together. First of all, for the carpet, so the first and the third picture you've already seen. There is one extra panel here, and what is presented on the second panel, it's it's actually scaling of the density of states as a function of system size. So we know that on average, the density of states should scale with respect to the dimensionality. So in that case would be 1.89. However, what we can see is that for some regions, if we energy resolved this density of states scaling, we can see that it's smaller than the value that is on average, that is Hausdorff dimension. And this nicely coincides with a non-trivial Chern number. And here I'm showing the results for the disorder calculations. So please take a look on those two arrows. There are two scenarios that we can actually follow. And if we are starting from a trivial region, like here, when the Chern number is 0, and we perform those calculations with disorder, we see that the value of the variance is almost all the time quite far from this predicted for Wigner-Dyson. So we can say basically that like system is really quickly in a trivial phase. However, here this is a completely different scenario. So we are actually going through a region in which the states are really delocalized. And what is very important to add is that this disorder strength is far exceeding the energy scale of the problem, because the energy scale is given just by the Hopin integral T, which we set to 1. And this is also a very interesting signature of quantum Hall system. The same we can repeat for the gasket. And basically what you can see that the results are less clear, however somehow consistent. And the question is why it's the reason why the results are less clear to identify. One may say that perhaps this is the effect of finite size, of the finite size. But if this were be the effect of finite size, then we would have deviations over all energy ranges, and still we somehow see that there are some quantized regions. So perhaps the reason behind that is just the dimensionality, that is not 2D anymore. So just to sum up, using complementary tools, that is level spacing analysis, real space Chern number calculations, and also H-states localization properties, we identified states which behaves quite similar to what we know from quantum Hall systems. But this was realized on the lattices, which are characterized by non-integer Hausdorff dimension. And there are open questions. As I said, this field still remains not very understood still. So first of all, it would be nice to find like a general classification scale for the fractals or for the system, which are scale invariant. So not translational invariant, but scale invariant. And the open question is also about the interaction and the effect of whether we can have like a topological order to build topological order. With that, I would like to thank you for your attention.
For your talk.